So our first topic is sets. So if we want to define what a set is, a set is an ordered collection of objects. So we have notations that represent sets. You can represent sets as follows. You can use the brackets like that. So you can, all these notations refer to the same set. 1, 2, 2, 1, 1, 2, 1, 2. X such that X is an integer, which is greater than or equal to 1 or less than or equal to 2. All these refer to sets. All those refers to the same set 1, 2. Okay. So we will encounter the following notations in sets. We have that notation. Which can also be written like that. And it refers to the empty set. And then we have that notation. So these are always written in Roman notation. So that is the set of non-negative integers. That is a set of non-negative integers. Then you have that one, which is equal to 1, 2, 3. That is the set of positive integers. Once more, share your gadgets with your friends so that we can all fit in this class. So this is Z is a symbol. As I've said, they are always written in Roman symbolism. The set of integers has the negatives, 0, 1, and the positive integers. This one is just the set of non-negative integers, set of the positive integers, and this one is called the integers. Okay. Sometimes this one is known as natural numbers. Okay. The difference between non-negative and positive integers is that the non-negative integers have a 0. The positive integers do not have a 0. The integers have the negatives. Okay, so that is a difference there. So Q is P over Q, which is equals to A over B. A, B being members of the natural numbers, and b not being equal to 0. So when we have these numbers, we call them the rational numbers. Knowing these numbers is important because sometimes when we are trying to answer questions later, maybe inequalities or functions, specifying the nature of the numbers affects your answer. Okay. So very, very important that we know these numbers. Yeah, so rational numbers, any number that can be written in the form of P over Q or A over B, where A and B are members of integers. A and B can be either of these, but not equal to 0. B, this B should not be equal to 0. We refer to these as rational numbers. Numbers that can be written as fractions, rational numbers. Okay. So this could be, rational numbers could be a number like 1 over 2 is a rational number. 2 is a rational number. 0.333 is a rational number. They all can be written as fractions, okay? You can rewrite a decimal number into a fraction. 2 can be written as 2 over 1, so it is a rational number. A half is already a fraction, so it is a rational number. The positive rationals, the denominator is just greater than 0. Where Q is a member of the rational numbers. And Q is greater than 0. So like if you're looking at the positive rationals, this Q is greater than 0. But the other rationals, the Q is a member of integers. Integers can be negative. Only that Q must be greater than, must be not equal to 0. So it can be less than 0. It can be a negative value. Okay. Then you have real numbers. Real numbers are rational and irrational numbers, are real numbers. So the positive reals are rational numbers which are positive. So then we look at what we call set cardinality. So the cardinality of a set A is the number of distinct objects A. Objects in A. And it is written symbolically as it has two lines, the cardinality of A. So when A is a member of the natural numbers, then it is a finite integer. When the cardinality of A is a member of natural numbers, then its cardinality is a finite integer. Otherwise, it is cardinality is just the size of a set. We'll look at size, it's just the size of a set. Okay, just the size of a set of the elements. For example, if set A is equals to this, then the cardinality of A written like that is just 3. A minute, just a minute. Yeah. Cardinality is 3. Then we look at set equality. A is a set. Set A is equals to a set. We've defined a set as what? A set is an unordered collection of objects. So set A has the 3 objects, 1, 2, 4. The cardinality of set A is the number of objects in A, written objects. The number of written objects in A are 1, 2, 3. So the cardinality of A is 3. Why can't you see clearly what is on the board? This one who can't see clearly what is on the board. What is hindering you from seeing what is on the board? Hmm? And another one is asking, why do we say that the cardinality is 3? Because we have defined what cardinality is. That is why we are defining these terms, okay? That's why we are defining the terms. The cardinality of a set A is the number of distinct objects in A, written as that. So we are coming from this definition. We are not just saying them after, we say them after defining. So you better be keen, members. We are not going to be repeating this. And anyway, we have the Zoom recorded. So if you miss continuously, just go to the Zoom. That is the advantage of the Zoom record, okay? So we have defined what a cardinality is, and that is why we are calling the cardinality of this set A, written as that, cardinality is written as that to be 3. The number of distinct objects in A are 3, okay? Rewind, you can rewind, but I've rewinded. The good thing of recording is you'll rewind. So like the finite, we have said, if that number, if this number is a member of the natural numbers, okay? If the cardinality like this one is a member of the natural numbers, then it is finite. If it is not a member of the natural numbers, then it is infinite, okay? Yes, thank you. So then we can look at the next part of this. Something called set equality. So not the definitions will guide you, okay? Two sets S and T are equal, written as S is equal to T. If S and T contain exactly the same elements. Okay, so these sets can only be equal if they both contain the same elements, exactly the same. That is, for every X, for every given X, where X is a member of S, then X is also a member of T. Not the symbol. The symbol, the arrow is both ways, okay? That arrow is both ways. If it is both ways like that, then it means that two sets, the set S and T are equal. For example, if set A, if S is equals to 4, 5, 6, and T is equal to 5, 4, 6, then sets S and T are equal. The members in set A are the same members in set B. So those two sets are. But we need to understand the symbols that are used, okay? So as you study sets, the symbolism is important. Then we have subsets. A set S is a subset of set T, written as if every element in S is also in T. I.e., for every X, a member of S, implies that X is a member of T. So this definition of subset is different from the definition of equal. The arrow only points towards one direction, not both directions. So you differentiate that. Okay, for every element of X in S, this element is also found in T. It means that elements in T are not necessarily found in S, but elements in S must be found in T. Then S becomes a subset of T. Then set X is a strict subset of T, written as if S is a subset of T and there exists some element X So a set is a subset of set, a set S is a subset of set T, written as that. If every element in S is also in T. For every X a member of S? They are found in T. We'll see examples, so don't worry. And then we have strict subsets, okay? Set S is a strict subset of T, written like that. Strict subset is written differently from this. If S is a subset of T and there exists some element X in T such that X is not in S, then it becomes a strict subset of T. There's some element here that is not here. That is when we say S is a strict subset of T. So we look at examples 1 and 2. Set 1 and 2 is a subset of that set. Set 1 and 2 is also a strict subset of 1, 2, and 3. Strict because 3 is here, but it is not here. That is a definition of a strict subset. There exists an element X, which is a member of T, such that X is not a member of S. When that happens, then S is a strict subset of T. 1, 2, 3 is a subset of 1, 2, 3. But 1, 2, 3 is not a strict subset of 1, 2, 3. It's not a strict subset because we don't have an element here that does not belong here. Okay, all elements in S belong to this one. So this set S is not a strict subset of this one. So for any set S, the empty set is a subset of S. So that is very critical for us. We will be looking at the power of a set. Rewind. Kama uelewi utapata zoom rewind. But I'm trying just to give this example according to the definitions. 1, 2 is a subset of 1, 2, 3. From the definition, a set S is a subset of set T written as that. If every element in S is also in T, every element in this set is also here. So this set is a subset of this one, following the definition. This one is a strict subset. 1, 2 is a strict subset of this, following the definition. Set S is a strict subset of T, written as that. If S is a subset of T, this 1, 2 is a subset of this, okay? And there exists some element X in T, such that X is not a member of S. That is true. 3 is in T, but it is not in that. So it has satisfied the conditions for a strict set. 1, 2 is a subset of 1, 2, 3. And 1, 2 does not contain 3, which is contained in 2. Therefore, it satisfies the definition of a strict subset. And so it is a strict subset. 1, 2, 3 is a subset of this one. Because for every X in S, X is also in T. 1, 2, 3 is in S and 1, 2, 3 is in T. 1, 2, 3 is not a strict subset of this one. For it to be a strict subset, one element is T must not be in S. But here all elements in T are in S, so it cannot be a strict subset. Yeah, good. That's even better. But as I've said, there's always the recording. No, not always. Okay. So a subset can be strict and also be not strict. Yes, it can, but not always. And that is why we have two examples. This one is a subset of this, but it is not a strict subset. Okay. So it's not always that if this is a subset of this, then it will be a strict subset. Because like in this case, this is a subset of this, but it's not a strict subset. Because for it to be a strict subset, there has to be an element in T which is not in S. But here, all elements in T are in S, so it is not a strict subset. This one is a subset of that. 1, 2 is a subset of 1, 2, 3. And because 3 is not in 1, 2, then it is a strict, it's also a strict subset. Okay, so that differentiates them. Now, there's no difference between face-to-face and not face-to-face. You can see my face, okay? And so the most important thing here is that blackboard, okay? My face does not show this. The blackboard here shows what I am talking about. So it's not about being face-to-face, okay? So learn to understand this. The blackboard here is very critical. Whether I am in a face-to-face situation or not, I will use the blackboard. So the blackboard is important here. And as you've seen me, those who are here early saw me, okay? So the advantage is we are zooming this, isn't it? It is on Zoom. So if you were face-to-face, would not be recording this. The advantage is it is going to be recorded and you'll just rewind it until you get the point. So for any set S, the empty set is a subset of S. That is important. When we are looking at power of sets, an empty set is an element of a set. So when we'll be looking at the powers of sets, you'll find that we'll include the empty set and the universal set, which are all members of the set as an element of a set. Okay. So this S, we must not always have S and T. These are just symbols. It can be A, it can be B, it can be C. Okay. So it must not be S and T. Okay. So as I've said, the advantage we have with this, and that is why I like face-to-face, is that you can rewind it and you can be able to understand it better. So for every set S not equal to the empty set is a strict set of S. For every set that does not contain the empty set is a strict subset of S. Okay. Because if S does not contain this, then the empty set is a strict. So there's an element in S that is not the empty set. So a lot of mathematics, sometimes you cannot understand them on the first, when we first describe them, but that is why we have Zoom. That is the advantage of this. If it was face-to-face, there's no repetition of this. It is, you understand, and we cannot keep repeating. You have to understand the notes, but for this one, the notes come with the Zoomed class, which you can understand. So S is a subset of T, and T is a subset of S if and only if S is equals to T. That is when we can have the two situations. Empty set is a set that has no items in it. Okay, that is the empty set. So we can look at set operations. Hmm. So members have said the advantage we have with this class is you can go and rewind. There is something called rewind. So like to learn online, you'll always get a rewound of it. Otherwise, if we keep repeating this, we will not complete this class. For every set, S is equals to the empty set. The empty set is a strict set of S, okay? For every set S, which is not equal to the empty set is a strict subset of S, okay? Because this is not contained in S, and therefore, it satisfies the condition that it is a subset of S, but it is not contained in S, okay? It is, by definition, it is a subset of S, but because of this, it is not contained in S, then therefore it is a strict set of S, as opposed to a subset. Because from here, we are saying that in this case, S is not equal to the empty set. And if S is a subset of T, and T is a subset of S, this can only happen if and only if S is equals to T. If T is equal to 1, 2, and S is equal to 1, then S is a subset of T, and T is a subset of S. That only happens if S is equals to T. If T is equals to 1, 2, 3, and S is equals to 1, 2, S is a subset of T, but T is not a subset of S, okay? Because 3 is not contained in S. So that is why we are saying this can only happen. This situation can only happen if T is equal to S. Otherwise, if it is not equal to S like we have here, then T cannot be a subset of S. and S be a subset of T. So an empty set is a set that does not have items in it, okay? It's just the way the word reads, empty set. It does not have elements, okay? So set operations, we have certain operations in sets, which we, okay, that's okay. We have operations in sets. So we have the union of a set. When you merge sets, merging sets leads to set union. When you want to merge two sets, you call it set union. When you identify the objects in common, then we refer to that as set intersection. When you identify the objects unique to one collection, then we refer to that as set difference. No, it is not that symbol you're using. Remember the symbols, like whatever you're using there is not what is given here. These symbols are unique, okay? That is a curve and a line, not a less than symbol, okay? This is curved. So you will check these symbols when I give you the notes. Huh? The symbolism is important. If you identify the objects unique to one collection, then we look at it as set difference. Then we may be So we may also be interested in knowing all possible ways of picking one object from each collection. So that is referred to as Cartesian product. All possible ways all possible ways of picking some object from just one. It's called power set. I like those answers. Those can't get me. Nunua bundles. Kwa sababu wengine wanaelewa. All possible ways of picking some objects from just one of the collection is called power set. So we are going to look at each one of them. The good thing is we will be looking at each one of them. Power sets, we'll write them out and then we will look at examples. So even as we write the symbols, we will also look at examples in each case. So the power of a set S is the set of all subsets of S. You'll understand. You'll understand. So far, we have understood the others. So power of a set P is the set of all subsets of S. Okay. We'll explain with an example down there. We have looked at what a subset is. So if you're given elements in a set, the power of a set is the set of all subsets of S. Get all subsets in a set S. That gives you the power of that set. So we'll see what Cartesian is. These ones, they are just matched. Cartesian product is just a cross product. if you're given S and T's in these two sets, you just cross them. S is a member of S, big S, and T is a member of T, which means you're just picking S from the bigger set. The small s, which is an element of S, you're picking it from the bigger set, and the small t, you're picking it from the bigger set T. That gives you your cross match. This cross is a cross match of the two. And of course, when we are applying sets, it is used in matchmaking. Okay. We'll see that in the examples. So the symbolism for union is S union T. Symbolism for cross product is S with that cross T. Power of a set, that is a symbolism. So we are looking at the symbols. S union T is just merging them, written as X, such that X is a member of, or. The word or is synonymous with union, or X is a member of T. It can be in S or in T. So you pick all elements that are in S and that are in T, but you don't repeat them. Okay, you don't repeat them. If they are both in S and T, you don't repeat them. So symbolism for intersection is S intersection T, which is equal to X, such that X is a member of S and X is a member of T. And it has to be in both S and T. That is when it is an intersection. And we refer to it as sets set of elements in S and T. So union is, it has to be in S and T. I mean, intersection is, it has to be S and T. Union is, it has to be in S or T. Difference, X such that X is a member of S, but X is not a member of T. So this is a set of elements in S, but not in T. Yeah, that's the difference. And very, very critical in sets. The and the or, intersection and union are very critical. Even the differences, and you're looking at this, you learn later, discrete mathematics. All these will empower you. So these things really seem to be basic or abstract, but it's important to understand them from the simple point of view, because later on we'll be using them. Um, and the basis of mathematics is just that, looking at elements in a universal set, and also not looking at elements in it and how then you can merge them, okay, together, okay, or get common elements within them, or elements in A and not in B, or match, make the map, okay, cross them. So just getting to understand these symbols and how they're used is very important. So S complement is just X, such that this X is not a member of S. So this only happens when we are talking about universal. We have to have a universal set to see this picture. So universe means the whole set. You normally have the whole set. If you have S and S, this is S, and you have, yeah, you have 1, 2, and you have 3, 4. Okay, so S is equal to 1, 2 elements in S. So the complement of S will be equal to elements not in S, which are 3, 4. So let S be equal to 1, 2, 3, and T be equal to 3, 4. B will equal to A, B. Then PT will be equal to the power of T. So the power of T is all subsets of T. All subsets of T include the empty set. The empty set is always a subset of a set. Then 3, 4, then 3, 4. 3, 4 is the universal set. 3, 4 is the universal set. So the power of a set is all the subsets of the set. The empty set, 3 is a subset of T, 4 is a subset of T, 3, 4 is the universal set, which is also a subset of T. So that gives you the power of T. Then we have S cross V, Cartesian. So S cross V is just crossing S and V, S and V. V is AB. So crossing S and V will give us 1A, 1B, 2A, 2B, 3A, and 3B. That is Cartesian products. We are just crossing, you see, 1A, 1B, 2A, 2B, 3A, 3B. You're just crossing S and V, okay? It's like you're matching them, okay? It's like you're matchmaking. Thank you. Then we have S union T. S union T. S union T is just element in S or T. So we'll have 1 is in S. Although it is not in T, it is in S. 2, 3, and 4. That is S union T. Remember, we are not repeating 3. Once you have one of what is in either, you don't repeat it. Okay? And then we have 4, which is in T, but is not in S. Then we have S intersection T, which will give us what is in S and it is in T and. So what item is in S and T? What item is in S and T? Three. So 3 is correct. S not T. What items are in S but are not in T? One, two, that is correct. You can see now you're getting everything, okay? So if we are dealing with a set of all integers, if you're dealing with a set of all integers, S complement will be equal. Remember, our S is 1, 2, 3. So S complement is any of these integers which is not in 1, 2, 3. Okay. So we'll have everything negative, -2, -1, 0. And we avoid 1, 2, 3. So we'll have 4, 5, and so on. Okay. So if we bring that up, you have S complement to be equal to all negative integers from infinite to -2, -1, 0. Then we cannot have 1, 2, 3 because 1, 2, 3 is in S. We are looking for elements that are not in S. So we have 4, 5, and so on to infinite. So that is S complement. All integers except the ones that are in 1, 2, 3. So that is why I indicated to you that defining sets is important. Notes are there, you get notes. Defining sets is important. Once you define it as the set of all integers, then all integers are involved, and you can see our set involves all integers. So we can always use Venn diagrams to visualize some sets, set manipulation. I just indicated that, you see, integers, a set of all integers is a set of all integers from infinite negative to infinite positive. That is why we are putting dot, dot, dot here, referring to all the infinite negative values. Then we narrow down to -2, 1, 0. Then we avoid S. 1, 2, 3 is avoided because we are looking at sets. The complement of S are sets of objects not in S. So that's why we have not put here 1, 2, 3, 4, 5 to infinite is this S complement set. So we can manipulate sets using Venn diagrams. We look at a theorem where you're not using the Venn diagram and then you're using the Venn diagram. Sometimes Venn diagrams make it easy to State operations using Venn diagram. So we can state a theorem such that we say, yeah, you'll see these, if I teach you discrete mathematics, you'll find us stating theorems and proving them, which we are going to do now, but we'll use both Venn diagrams and um, not using theorizing it. That is something you expect because this is a higher level of learning. You have just been doing mathematics without really studying the origin of this mathematics. So theorems were the origin of a lot of mathematics. Somebody has to theorize and then prove the theorem. It's only when you prove the theorem that it can be applicable. Otherwise, if you just state something and not prove it, in many cases, it will never be applied. So a lot of people who theorize then have gotten PhDs and so on, because then you have a proof for your theorem. So most of the time you find that anytime you're applying a concept in mathematics, you have to prove it. And there will be a lot of proofs before you apply the concepts you undertake in mathematics. But you'll realize that at KCSE level, you just used these concepts. You never proved a lot of them. There are a few that you proved, but a lot of them you're just applying them. In this case, because you have the students who are further in mathematics, you have to understand the origin of these concepts and prove that indeed they are true. So you should embrace that you are a better person because people just use them, but now you are understanding their origin and you are able to prove that they really work. So you need not fear that, but you need to embrace that differentiates you from just a common person who manipulates the mathematics to somebody then who can be able to prove that these theorems work. So learn to be the better person. Don't fear to be that person because then you differentiate yourself. So we can state a theorem. Yeah, it comes early because we just want to see how Venn diagrams make it simpler than just being able now to go through the process of proving. It's better you use the Venn diagram. So there's a theorem 1.11 that states for all sets, for all sets S and T, S is equal to S intersection T union S minus T. So we have looked at this symbolism for all sets S and T. S is equals to S intersection T union S minus T. So we'll prove without using Venn diagrams and we'll prove using Venn diagrams. To formally, without using Venn diagrams, to formally prove the identity we will show both of the following. S is a subset of S intersection T union S not T and S intersection T Given S minus T, the subset of S. Remember, we stated that this can only be equal if S is a subset of S intersection T union S minus T, and S intersection T union S minus T is a subset of S. That is the only way these two sets can be equal. But we want to prove that is true formally. So first of all, we can prove the first one, then we prove the second one. I assure you they are not things that should worry you. If X is a member of S, then either X is a member of T or X is not a member of T. Okay, so if X is a member of S, then X could be a member of T or X could not be a member of T. If X is a member of T, then X will be a member of S intersection T. It follows. And thus also X will be a member of S intersection T union S minus T. So if S is a member of T, then if X is a member of T, then X must be a member of S intersection T because X belongs to S and T. And thus it will be a member of X. X will be a member of S intersection T union S minus T. Okay. S minus T means X is a member of S, which is here. X is a member of T gives us X is a member of S intersection T. The other scenario is if X is not a member of T, then it follows that X is a member of S, not T. Okay. If X is not in T, then it follows that X is a member of S minus T because we had already indicated that X is a member of S. If X is a member of S and it is not a member of T, then X must be a member of S minus T. And thus also you find that so we have proved this one. For the two scenarios, we have proved that S is a member of. Then we look at the second one. We have proved this first one, then we look at the second one. If X is a member of From the second side, X is a member of S intersection T union S not T. Either X is a member of S intersection T, or X is a member of X is a member of S minus T. So if X is a member of S intersection T, then it follows that X will be a member of S. If X is a member of S minus T, then it follows that X is a member of S. So we have proved the two sides. We have proved that this is a subset of S, and we have proved that S is a subset of this, and therefore S is equal to S intersection T union S minus T. So this is proving it formally. If we look at using the Venn diagram, it becomes easier. Okay, so if we had the Venn diagram, then we'll have two items. This one S, then we have T. So this middle part is S intersection T. And this part is S minus T. Okay. So you'll find that S will be equal to S minus T so let me start with that tells you that S is equal to S intersection T. If this part is S, okay, that part is S, okay, then S is made up of S intersection T together with union, okay, S minus T. And you can write it the other way, okay, S intersection T or union S minus T will give you S. That is what gives you S. Yeah. So using the Venn diagram, when you just shade the two, they give you S. And it is easier to see it from here that S is equal to S intersection T and S minus T. This part gives you S. Okay. So this is a proof using Venn diagrams, which is easier. Therefore, in sets, Venn diagrams make your work, at least the Venn diagrams. You see, we agree. I'm sorry for those who cannot use the whole of it, because probably you're using fonts. But we will have the rewinded thing you can use. So that is what we are trying to say, that it is easier to use the Venn diagram. So I'll give you an example and then give you a few seconds to try it out. Then we can do it before we go for lunch. So let's So we let the universal set be then A then B then C. You draw a diagram. Label the regions and place each element. In the appropriate region. You will get the recorded. They will be on imasomo. I must share them. One of the conditions is we must share the recordings. So that is why I've told you face-to-face has one disadvantage, which you will not have a recording. This one you'll have, and you'll rewind or rewound it until you. So let us try this. Let us try this. Let us try and represent this on a Venn diagram. Yeah, even me, I cannot load for you the course outline. Did I share the course outline, members? Did I share with you the course outline? Let me share. Let me share. Did I share? Just copy this, then I'll share the course outline. It's important to have a glance at the course outline. Yeah, I'll share. It's important to look at the course outline so that you see it's what we've done. But look at this. I just want you to have a rough sketch of that. You need to have a rough sketch of that. So bundles, when you are at CUK, you can always access these bundles. And also I've said you can work as a team. Work as a team for it. You'll find later on, learning online is the best thing because you can always have this zoomed recording and you can always go through it to understand even further again and again until you understand. The first diagram is not difficult to understand. But there are people copying this. So you need to copy this because I want you to attempt this. Yeah, I want everybody to copy this. Make sure as you ask for that one, you've copied this because I want you to try that out before I give you an example. So has everybody copied this? Try this out. Wengine wamekopi. Wengine mmekopi. So this one, as I indicated, S. This part represents S, and that part represents T. S will be equal to S intersection T, and S not T, union S not T, gives you S. So without using the formal method, you have proved that S is equals to S intersection T, union S minus T. Okay. And at the same time, S intersection T union S just gives you the whole of S. So whichever way you start and go, you will have proved that this is equal to S. And you can see the formal one took us some time, but the Venn diagram to do it. Okay, so the Venn diagram is a simple way of doing it. This is 3, 6, 8, 3, 6, 9, 12, 15, 18. 12, 15, 18. Draw a diagram. So this is 15. Draw a diagram, label the regions, and place each element in the appropriate region. Yeah, so, oh, you've already drawn that. Somebody has done that. Who is the first person to do that? I want us to look at the course outline. The course outline has items that are familiar, so you will not have a big issue. Meanwhile, just draw as a source for this course outline. Let's draw. It's good to have a glance at course outline. So that is our course outline for basic mathematics. That is a course outline for basic mathematics. The purpose of basic mathematics is to introduce students to basic mathematical operations. This course acts as a bridging block between prior acquired knowledge and skills in mathematics and the expected knowledge and skills to be acquired. Notes are there. So the objectives, expected learning objectives of our course, to draw graphs of polynomials, equations of first and second degree, explain features of graphs and such as integers, vertex, slope line, or lines, undertake operations on functions such as addition, multiplication, division, composition, and finding inverse functions, solve problems exponentially and using logarithmic functions and sequence and series, solve a system of linear and quadratic equations. So the topics, the first topic we are supposed to look at is the sets, what we were doing today. Equations, linear and quadratic, equations, quadratic, linear inequalities, functions, graphs of functions. And then we have exponential and logarithmic functions, trigonometric functions. And then you have sequence and series and trigonometric functions when we end the course. So basically, that is how you're supposed to, how the course is examined. 5% is participation. So participation is important. 25 outline quiz, online quiz and assignment, important. End of session exams gives you 70%. So attending class is participation. You need to attend class. Therefore, that's how we'll administer. In fact, down there it is written that it is an online course. But we can still just do it both ways blended. So has somebody drawn that? Take a snapshot and share with us. Have you drawn that? Anybody who has drawn so that we see their snapshot? Someone is asking me what I do with the ABCD, and I thought you guys are through with that. Anyone who has drawn this, draw a diagram, label the regions, and place each element in the appropriate region. Anyone who has done this? Hmm? And then, you know, the funny thing is you're asking me. Members, I've seen many hands. Why is it that I cannot see any hand now? Huh? Anyone who wants to try, whatever it is you've done, just do and send me. Let me look at what you have done. Two people. Can you send me? You have been very active with words here. You have been very active with those words. Now what has happened? members. You need to get all the marks, all the marks for participation. So we have 3. Remember, the universal set is 1 to 20, but we have A, we have B, we have C. I hope they are big enough. I'm not seeing them being big. We have A, we have B. So it's very simple, this. We have A, we have B, we have C. In A we have 5, 10, 15. B we have. So the first thing we do is to find out which ones are intersecting. A is equal to 5, 10, 15, and 20. B will be equal to 2, 4, 6, 10, 12, 14, 18, and 20. And then C will be 3, 6, 9, 12, 15, 18. So this one here at the center here, we put what is intersecting in A, B, and C. What is common in A, B, and C? What are the values common in A, B, and C? Is there any value that is common in A, B, and C? No. What values are common in A and B? A and B? 10. 10 is common. Anything else? Yes, I've seen someone. 20. So we put 20 and 10 there. What is common in B and C? B and C? Mm-hmm. 6, 6 and 12. Any other? $18. 18 is also common. You can put a comma there. AC, what is common in A and C? 15. Okay. So once we have these ones that are common, then we can fill in what is in A other than what is already filled. A, we already have 10, we already have 20, we already have 15. What is left that is not filled in A? 5, so we fill it there, 5. B, what is filled? What is not filled? We have 6, we have 18, we have 20, we have 10. What do we have left? 2, 2, 4, 2, 4, 8, 2. Or do we have 8? 2, 4, 12. What else? There's one that is left. 14. I don't think we have 16. Just 2, 4, 12, and 14. I think those are the ones that are left. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. In fact, there are 8. Why do you have 9? Or 12. 12, 12. 12 is already done, so we don't need to do it. No, 14. Then we have C. C, we have 15, 6, 18, 12. What is left for C? 3 and 9. 3. So these numbers were 1 to 20. 1 to 20. Which ones are not filled? Okay. So we can check which ones are not filled by just numbering them. Is 1 among these ones? Number 1? Do you have number 1? 18 B. B has 8. Oh, I had left out 8. Sorry. There's 8 in between here. I've left it out. So B has 8. Thank you. Twelve we have already filled. 12 is common. So we filled it. Okay. So when we are looking at the universal set, yeah, it is common. It is common. No, it is not common, but it is in B. I had left it out there. So we want to, the universal set has 1 to 20. We are looking for those that are not filled from the universal set. The universal set is 1 to 20. 1 is not yet here, isn't it? 2 is there, 3 is there, 4 is there, 5 is there, 6 is 7 there. 1 to 20, we are looking for the elements that are not there. So we are starting with 1. 1 is not there. 2, 3, 4, 5, 6 is there. 7 is not there. So these ones are in the universal set. 7. 8 is there. 9 is there. 10 is there. 11 is not there. 12 is there. 13 is not there. 14 is there. 15 is there. 16 is not there. 17 is not there. 18 is there. 19. So those are the ones you keep in the universal sets. Okay. Which we are labeling as section 7. So that is how you come up with this. You can label each section accordingly. Okay. You can label each section. You can say this is 1, this is 2, this is 3. We have each section you have filled, you can label 1, 2, and so on. But that is the way you fill it. So you will give me a few seconds. Remember, we started late. I give you some homework. Huh? You go and do. Let me just write. The homework will not take long. Or I can just mount the the homework, and then you can I know it somewhere. Instead of writing it, maybe just a few seconds, I'll get hold of it, then you can. So this Zoom, it's a Zoom that is saved. So I'll just share with you. That is the example. You can copy it. Copy that example. You can do it as homework. It will help you. Now, don't draw in my work. All these will be on Imasomo. All these will be on Imasomo. The course outline, the notes, the Zoom, all of them, is good to get them from Imasomo. I know Imasomo is not active, but we'll make them activate it so that you get all this information. Kuna wale wanajua hata ku screenshot. Nice. But write this question, you go and work on it. A very nice question. If you're through, you can leave. Have a nice day and keep working hard. Answers wewe fanya, tutaangalia tukikuja. Which example? Which example now? Copy that question. So if you're through, you can leave. Members, you too, have a nice day. Make sure you copy that. Make sure you copy that. Make sure you copy this. You're welcome. Thank you too for attending. Keep working hard so that you don't get into trouble, soups and so on. These things you can do them. They are very easy things. You too. Have a nice lunch. Have a good day too. I hope we are all through. Mm. Okay. That's why I'm not picking it out. I'm not removing it until you all copied. Thank you. You're amazing too. You have participated. I've not seen people chatting the way you've done. So keep up, just keep working hard. Yeah, the notes, you'll get them. These are notes, you'll get them on Imasomo. Bye.